An alternative way in solving systems of linear congruences is actually backward substitution. And here again, you have the same example, and you start from the first congruence, x is equivalent to 1 modulo 3. This means I can write x as 3t plus 1, where t is some integer. 3t plus 1 is the general form that x needs to satisfy. And this means this should be congruent to 4 modulo 5 based on the second congruence. Okay, this means 3t is congruent to 3 modulo 5, so you just get rid of this one. And at this point, 3t equivalent to 3 modulo 5, you just need the multiplicative inverse of 3, which is 2 under modulo 5. That means t is an integer which is congruent to 1 modulo 5, right? Therefore, I can write t now as 5u plus 1 for some integer u. As I have seen, t is equivalent to 1 under modulo 5. This means since x equals 3t plus 1, right, I can write x as 3t plus 1 and t as 5u plus 1. Just plug that in here and expand this expression to obtain x equals 15 times u plus 4. And u here is some integer. And lastly, if you actually use this final congruence relation, this expression 15u plus 4 needs to be congruent to 7 modulo 8. Okay, so this means, well, 15u under modulo 8 is equivalent to 7u, right? Because you can just take out 8u because that is congruent to 0 modulo 8. And this 4 you take on the right-hand side, which makes it 3. So 7u is congruent to 3 modulo 8. And under modulo 8, 7 is the multiplicative inverse of itself because 7 times 7 makes 49, which is congruent to 1 modulo 8. And therefore, as a result, u must be congruent to 5 modulo 8. This means I can write u now as 8v plus 5 for some integer v. And then, since I know x is equal to 15u plus 4 and u has this form 8v plus 5, I just plug u in this expression and to write x equals 15u plus 4, which equals 15 times 8v plus 5 plus 4, which gives me 120v plus 79 as expected. And this means x is congruent to 79 modulo 120. So the solution is unique under modulo 120, but in the set of integers, of course, any integer satisfying this form, 120v plus 79 for v and integer, is going to satisfy the set of congruence relations. Now, in the application of the Chinese remainder theorem, the one important point was that these numbers, 3, 5, 8 in this example, has to be coprime. What if they are not? Suppose that this one is changed to 6. Okay, so now in this case, 3 and 6, they are not coprime, and also 6 and 8, they are not coprime also. So we cannot apply the constructive method in the proof of Chinese remainder theorem directly. In this case, while this is an important property, this system, such a system where these are not coprime, has a solution if and only if these are satisfied. A sub I congruent to A sub j modulo GCD of M sub I, M sub j. You see, this condition corresponds to, in this example, for instance, 1 and 4 are A1 and A2, is the pair 1 and 4 congruent modulo modulo GCD of 3 and 6. Obviously, the GCD of 3 and 6 is 3. So 1 and 4 are congruent to each other, modulo 3. So that is satisfied. So that is the condition you need to satisfy if this system has a solution. Now, in the general case, if these numbers are coprime pairwise, then by the Chinese remainder theorem, there is always a solution. But if they are not coprime, there may be cases where there is no solution. So let's see what happens when we change this 5 here into a 6. And let's apply, since we cannot directly apply the method with Chinese remainder theorem, let's apply substitution method. Again, x we can write as 3t plus 1 and apply that to the second congruence. 3t plus 1 should be congruent to 4 modulo 6. This gives us 3t is congruent to 3 modulo 6. Now, 3 under modulo 6 does not have a multiplicative inverse. There is no number when multiplied by 3 is congruent to 1 modulo 6. So we cannot solve this in that way. But it should be clear that any odd number for t here satisfies this congruence relation. Okay, so I'm going to write t as 2 times u plus 1 for any integer u. And therefore, x can be written by plugging in the t. You can obtain x as 6u plus 4. That is not surprising, and I could have written that directly from this. And the reason for that is, you see, 3 is directly a divisor of 6. Therefore, as long as this is satisfied, and then I don't actually need this one, because that is a result of the second one. Okay, and let's continue. And the next step, x equals 6u plus 4. This should be congruent to 7 modulo 8. Then this means I get 6u congruent to 3 modulo 8. Now, this has no solution because left-hand side is an even number, but right-hand side, 3 modulo 8, that needs to be an odd number. So this has no solution, and this is not surprising because while this condition is satisfied with the first two, but it is not satisfied with the second pair, because 4 and 7 here are not congruent to each other modulo GCD of 6 and 8, and the GCD of 6 and 8 is 2. 4 and 7 are not congruent modulo 2. And that is the reason we have this even odd discrepancy here. So this system of linear congruences does not have a solution. Okay. Let's change this problem, make this a 6, so that maybe it has a solution, because, well, in this case, now the condition here is satisfied. Therefore, we expect to find the solution in this case. Now, in this case, I'm not going to do the substitution. You can do it yourself. I'm going to show you how to apply Chinese remainder theorem in such a case where you do not have a coprime moduli, let's say. So 3 and 6, their GCD is 3. 6 and 8, their GCD is 2. 3 and 8 is coprime. So I can write this linear congruence as x is congruent to 4 modulo 2 and x is equivalent to 4 modulo 3, the prime factors of 6. And 8, I'm going to keep as is. I'm not going to write it as 6 mod 2, 6 mod 4, etc. If you have powers of primes, just keep them as modulus values. But if you have something like this, you can write this as these two congruence relations. Now, when you look at these four, this one and this one are actually equivalent, right? So I can eliminate one of them, and I'm going to write this one. And this one and this one, again, equivalent, because you see, this means x is equivalent to 0 modulo 2, which means x must be an even number. But see, that's also apparent here, because x is congruent to 6 modulo 8. That means x must be an even number. Therefore, I do not need this one, so I eliminate it, and I have x congruent to 6 modulo 8. So in this way, you can eliminate unnecessary congruences. And of course, if there is a problem with this rule, this procedure will also show that to you, so that there is incompatibility. In this case, we reduced our congruence relation, system of congruence relation, to this one. And now you see the moduli are 3 and 8, which are coprime, and you can directly apply Chinese remainder theorem, and the solution turns out to be 22 under modulo 24. So any integer of the form 22 plus 24k for integer k is going to satisfy this system of linear congruences. One final point to make here is that you see the solution is it's unique under modulo 24, and 24 is no coincidence here, because you see 24 is actually the LCM of these moduli values here, 3, 6, and 8. So that is the general rule. If the solution exists in this case, when you have non-coprime moduli, the solution is going to be unique under modulo the LCM. Now, this is the general case, and when you think about it, in the original Chinese remainder theorem, we said that the solution is unique under modulo m1 times m2 times ... mn, which is in fact equal to the LCM, since they are all pairwise coprime.